So everyone, let's get started. So hopefully you've had the chance to run the notebooks, a couple of notebooks in Unit 1. Let me get my screen. Now, so this is the introduction to Diffuser's notebook. And John Whitaker was also a guest lecturer in Jeremy's Fast AI course, kind of goes through these. The good thing I find in these notebooks is a couple of things. One, it really gives you examples of using the pipeline from the diffusers, which we understood all of the underlying workings of it, but we didn't spend too much time writing the API. And so this is a good kind of review/revision and reintroduction to the high-level pipeline. So I'm not going to go through each of the steps, if you will, but kind of touch on the big ticket items. As he mentions, he has good references in the read up or the readme Unit 1 and get up the different links to the videos, the basics of the diffusion models, which we have seen. You kind of add noise and then you remove it, the equations relating to that, the steps we take, loading the images, add the noise, read the noisy versions, evaluate how well the model does at denoising, and then use the information to update the model weights. These are the couple of notebooks we'll go through today. And then here are some additional links and resources. And if we look at the notebook, he just kind of gives the outline of the notebooks, setup, also helps to set up your own HuggingFace account as well as access tokens. You can use the login, log into it, grab it, and a couple of the support functions, mainly to show the image and make a grid. I haven't watched this video, but I believe it has to do with using Dreamboot to kind of create versions or images based off of your face, just on 5 photos. And here's an illustration. Again, I didn't run that given how much data it would download and the time it would take inside. But it's just something trained on Mr. Potato Head, and then you can give it a textual description of what you would like, and out pops the image. By the way, I just found out, I don't know whether any of you are already aware, but if you turn on Google Labs, I think you can do that by searching for labs.google.com, and then if you turn on the first option, which is generative images, it gives you like 4 different options. And if you turn the first one on, excuse me, then whenever you go to Google search, you can actually prompt saying, I want an image with, or draw me an image with, for example, a rabbit and a bear celebrating a birthday, and out pops 4 choices of images. So Google already kind of seems to provide this textual prompting support just in its ordinary search if you turn on the option of having generative support or help from labs.google.com, which I thought was pretty interesting. You can just create images based on your descriptions on the fly from Google search tab on your browser or window in your browser. And again, it kind of gets into the fact that this FKS token is used just a unique identifier for the novel concept, and you can play with what happens if you remove it and not. I didn't do this because I hadn't downloaded the image size and the time and so on. And then he goes on to do the basic API. And that's the handy part because we haven't played with this part. We did use it in one of the very early notebooks, but then we didn't. We were more involved in understanding all the details, which we will do even in these 4 lectures. But starting from the top, you just import from diffusers the DDPM pipeline. Here he's kind of trying to train something where he has butterfly images, but reduced to 32 by 32 size, so almost of the size of our fashion MNIST data set that we were so familiar with, because that used to be 28 by 28. Here he just has the butterfly data set at 32 pixel by 32 pixel. But then he downloads a pre-trained that he has already trained model and creates images and views the results. And what you get are this kind of images of butterflies. And of course, this is not as, it's 32 by 32, and he is using a pre-trained model, not the same as using actual Dream Booth to produce, for example, the Mr. Potato image. Nevertheless, you can see these are clearly images of butterflies. And what you do, and again, we are very familiar with the steps by now, right? Loading some images, add noise, feed the noisy version, evaluate how the model does some denoising, and then use this information to update the model weights and then go through the essentially what diffusion sampling is. And then we sample from this trained model and package everything into a pipeline that that you can then upload the entire data and the pre-trained model onto Hub. So this is based off this collection of 1,000 butterfly pictures, and you go through and use the data set of HuggingFace. So from the Hug and Sonian butterflies subset, or you could do, I haven't played with it, but definitely intend to, you could load all of your images to a local folder, for example, some theme. It could be, pictures of favorite animal or some kind of Pokemon or whatever, and then load it into your local folder and then go do it that way, or you can use HuggingFace GAN. And again, the important thing though is you need to image is small, otherwise the training will be very long. And then you define the augmentations here, just resizing the image, randomly flipping it, in this case just horizontally, because if you do anything else, the butterflies get butterflies anymore, and then you transform to tensors, and then you just normalize. Here, interestingly, he doesn't do the, what Jeremy talks about of getting from 0.5 to 0.5. So that's another thing we may want to try, is he's sort of mapping it from -1 to 1, which is a range of 2. And we saw that a range of 1 actually helps things better, but you don't see too bad results even get this. But that's another thing to try, is maybe change the normalization to make it go between -0.5 to 0.5 rather than -1. Would be something like, what he does, multiply by 2, or very different ways to get it to, by adding 0.5 to each of, adding 0.5 here and subtracting 0.5. adding 0.5 to the min and subtracting 0.5 from the max. Then you transform the image and use the data set transform method, and then load the data. We just kind of see the data, if you will, and you can see that there are images of this is just you've just loaded the data and you're just watching. They have done nothing related to fusion yet. So just printing 8 images of butterfly. And then this is the interesting part. We've kind of seen this in much more detail from diffusers. You can import the DDPM scheduler. Let's see, there is an entire, all of the different diffusers that are available in the DDPM library. So you can see this DDPM scheduler, there's a DDIM scheduler, and all these different schedulers and the relevant code, how you use usage steps. So that's in itself is pretty fascinating that there are so many different schedulers. And by the way, it's a good thing that we got introduced to the concept of mixins as well in one of the, if you recall, in one of the lectures that Jimmy had of how to use mixins, where you're kind of adding or enhancing functionality, combining two different classes, how that works. So the code is in the form of mixin, is code for scheduler. The scheduler mixin contains all of the common functions shared by all schedulers. And then there is a config mixin, which actually gives the options, if you will, for each of the schedulers and puts that into the init function of the scheduler. So I haven't played with this a whole lot, but something, an additional thing to play with. Here he just uses the DTPM scheduler and just default uses 1,000 steps. These are equations we are familiar by now. And here is a plot of the classic DDPM scheduler. And like I said, I also kind of wanted to plot the DDPM scheduler, but with a beta schedule that's the cosine schedule, and here's the plot of that. And you can see that, you know, unlike this, which has like a steep part here and then a flat part here, you can see that this is much more smooth and doesn't have as much of a flat region here. Same with the square root of 1 minus alpha bar t as well. A little bit flatness here, but otherwise it's kind of fairly much smoother. And you can see the extent of the flatness here compared to this part. And then you just define a noise scheduler with 1,000 steps, and then, you know, define the time steps, define the noise, which is random. And the important thing here he points out is he uses, it becomes relevant, I believe, in the next notebook or later on in this notebook, I forget, but he uses random normal noise, like what you have in the batch. Then you add the noise to the images along with the time steps and print them so that, you know, and show them. So you see the various noised images. And since there are 8 images, each of them noised to a different random. And so you can kind of play with the different noise schedules and parameters, and then you can also watch the linked video. There are 2-3 videos that are linked, and here are the ones. I haven't watched them at a line out of time this week, but again, I think it's going to kind of go through them and get perspective different people explain. clear up certain parts of confusion that. And then he defines the unit model. Again, we've seen this in very gory detail. How this works. So the forward part storing, he just uses a simple list to store the data that he then forwards. Several drops of ResNet, downsampling it, and then forward passing it, and then upsampling it again. And he uses the unit 2D model. I think I have. Here is the unit 2D block code from users, models, and then unit 2D blocks. On block, ResNet downsample, block 2D, attention down block 2D, cross attention down block 2D, simple cross attention. So there are various out there in GitHub that you can probe to any level of detail that you're interested in. Here he just uses simply 2 down blocks and 2 attention down blocks. The 2 down blocks I could imagine would take you down 2 from 32, so you'd be down at 1. Then 8, and then you use attention down block 2D. And you use the same corresponding attention up block 2D for the first 2 up blocks, and then use just simply up block 2D for the remaining, and this is the simple, very simple unit 2D model. And of course, he points out that, if you're dealing with 512 by 512 and stuff, you'd want to make this much more complicated model, but just pass the data through, ensure that you get the same data out as what you put in, and then create a very simple training loop. And, the other thing I like about these notebooks is it also helps you kind of, at a very basic level, just using PyTorch, not using any of the callbacks and any special tools we have learned about or become familiar with in mini AI. This is very simple PyTorch code. So, that's another advantage, that all this can be done with very simple PyTorch-based code as well. So you define the noise scheduler, define the steps, choose the data schedule, define the optimizer, define a test for losses, and then train. And basically for 30 epochs, so you're doing 30 epochs training. For step and the batch, and you just grab a batch of images, which are your clean images, and then you define a rand n noise in the same shape, move it to the device, define the batch size, time steps. You randomly pick time steps between 0 and the number of training time steps. Pop size, batch size, right? Because you need to apply it to the 8 inputs, which by this batch size, and make them into log. Don't know why you have to make them into log hints, but I've seen that many people do this. I don't exactly know why. And then add the noise. So based on the scheduler, right? So noise scheduler, and then add noise to the clean images. You provide the noise, and you also provide the, or basically what this does is it, based on the time steps and based on the scheduler, a particular amount of noise is added to the clean images. And then get the model to predict, let's see, or give it the noisy images and get it to predict big equals false, I believe, instead of, in HuggingFace, as we learned, it returns big. So you say don't return a big, but return a tuple, and then grab the first value of the tuple, which gives you the value of the noise. And then do the loss, backward prop, add the loss to the list that you created, step the optimizer, zero the grad, time, and then just print loss after every epoch. So you do 5 to 15 and any for 30 epochs, then plot loss and see it go down. And if you didn't want to train this, you could kind of use this pre-trained unit, if you will. Then now that you've trained the model to predict the noise, you use the same model to denoise. Right? So you just create a pipeline. The model is your unit, or to the unit of the DDPM pipeline, you pass in your trained model and the noise scheduler, and you define pipeline output to be the image pipe and grab the image pipes dot images attribute and the zero value, and out pops the image of a butterfly. You can save the pipeline that you just trained onto a local folder, and what it has is the JSON file scheduler, because it needs to know the scheduler in order to be able to sample, because it will go through the same steps in reverse, if you will, as it were. And then the unit that you trained. The unit and the points out the scheduler and unit folders kind of have these config JSON file. And he said something about a bin file, but what it eventually currently does is takes it as safe things. So these give you everything you need to recreate the pipeline. And then you can just upload these because you've now trained them. You've now trained the pipeline on the butterfly set of images. So similarly, you create your own custom pipeline trained on whatever set of images that you would like. And that way you can then produce images or sample images that you want from them. And here's a sampling loop. And what I found is this image pipe.forward. I couldn't see the forward function, so I just had to look at the pipe itself. And this is something, again, we've seen, right? You define the sample to be some random, just defining a random starting point, and then even the time steps, you have an index and the actual time step. And with no grad, you define the residual to be, you pass this random value and the time step through the model. And then, as we learned, you have to do dot sample to grab the output. So the output of the model becomes pure. And then you pass the residual, which is the output of the trained model, the time step, and a random starting point, which is the sample, to a step of our scheduler, and then grab its previous sample. And that becomes a sample. You kind of go through this loop repeatedly, pass it to for the number of time steps. So it's 1,000 time steps, and we go through the sampling process. This is obviously depends on the scheduler, on what kind of noise is added and at what time step. And then you show the images and you get back. These are then the diffusion produced images. It looks pretty good and similar to our original set of 32 images. So actually, something else you can play with, since we know the feed code and stuff, we could kind of port it from the AI and try to calculate the fit score as well. Be an interesting exercise to do. And the noise scheduler step function does all of the math that's required to sample the denoising process, if you will. And then this is the whole thing where there's a lot of research. I think I posted a paper where people have brought it down now. I haven't played with that, looked at the code or the paper in detail yet, but I think I posted it last week. I think some folks from Google have brought this down to like 4 steps, if you will, by adding distillation steps on, as compared to, for example, in this case, we're using 1,000 steps. That's one of the drawbacks of this whole diffusion process compared to GAN. However, GANs are very hard, notoriously hard to train, very finicky, whereas diffusion process seems pretty robust and gives excellent output. But the disadvantage is it takes a number of iterations. So the iterative refinement process is fundamentally iterative. So that's the drawback. And then you can push your model to the hub and create a model repository, create a path and all that. The one thing and then obviously you say, hey, this is something we did, very basic training loop, right? So it was very simple. This is all the training loop was. And it was kind of really trivial training loop. And then he points out that you can use the training script that HuggingFace provides. And before that, you can point it, once you've uploaded your pre-trained model to the hub, you can use from pre-train method of the DDPF pipeline and download the model and use it to just generate images, which is these cells. And then using accelerate to accelerate is a library in HuggingFace, and using that to train much more complicated models. However, when I tried it, and I don't know whether you or mine have had a chance to run this notebook, but I ran into some trouble. There was it was able to download the model or download this, but I think I need to do something else in the accelerate. I have seen some notebooks which have accelerate config and stuff, which I didn't do, but when I tried to just run it as he illustrated here, I ran into some problems. There's an import error. It requires a source install, and some version issues and stuff. I didn't bother debugging. Probably.
Yeah, there's a line there inside it that says check min version of this repository of a diffuser repository, and it is specified as 0.22.dev. So it checks whether this is the minimum version or not. So it runs on the basis of that. So you have to comment that out.
Comment what out, Mike?
There is a line inside the train unconditional.py that says check min version of this diffuser.
So you're saying in the file that we download this file, if you comment out a particular line, and when you do that, then it runs successfully?
Yeah, it runs successfully.
And then basically it's just again, and you could probably, as it says here, provide some additional values which aren't supplied by which it expects but uses default values, but you could be more explicit and stuff.
Yeah, because it says here that it wants a source version of the Hugging Face diffusers,
Right.
which signifies us to the dev version of that particular library.
And then just push it and plot. And you can see that when you do much more complicated training than the very simple training we did, you can see the quality of the images improve very substantially. You can compare this. Again, an interesting exercise would be potentially to do the FID for these images compared to the FID for these images and see how much better is the accelerate training compared to the simplistic training loop we have. That would give you some level of the quality difference between these set of images which are trained with a much more complicated training loop, 45 minutes, whereas we just train for like 10 minutes. Of course, one thing I curious about is how many epochs that this thing trained for. Oh, 50 epochs. We only trained for 30 epochs, so there's an additional 20 epoch gain there, but there's a lot more differences in what we did. And then you can upload those. And then he gives you a whole lot of ideas of what you can do. This is something, again, that would be cool to play with. There's a notebook that you can use to create your own custom diffusion pipeline. That's something I definitely intend to do. See whether which one. This is the diffusers training example. Training. Yeah, this is the dream boot fine tuning for stable diffusion using diffusers. So this would be kind of a cool thing to play with by just using 3 to 5 images. You can train, take your pet, 4 or 5 pictures of your pet, and then you can have it do it in a variety of different situations. How do you get that done? Is what this notebook illustrates. That'd be a cool thing to play with as well. And then we kind of also look at the second notebook. The annotated diffusion variety of notebooks. So this is the diffusion model from scratch. Notebook, it's even simpler than what we have been exposed to so far. That's in a way I like the fact that the version I have. And we just again do the standard installations. The data set, in this case, he uses, instead of even fashion and Misty, just uses the same figures data set, loads it, no enhancements, no augmentations, nothing, just be transformed to tensors, grab a batch size of 8, kind of print them. And as we are familiar with fashion image, it's 28 by 28 pixels. And the other thing I like in these notebooks, it keeps it basic concepts extraordinarily simple. So in the corruption process, all he does is creates a noise, and then to noisify, it was the noisify process or the noisify function call in the mini AI discussions we have. He just uses a very, very simple way to noise or noisify the images, which is he just says, let me just add, if I give you some amount, then I'm going to subtract 1 minus the amount of the current image and the amount times the noise and add that. And that becomes my noisy image. And so this simply says if the amount is 0, then obviously you don't add any noise and it's all the input. And as you increase the amount from 0 to 1, if it's 1, then it's all noise, as you can. If it's 0, then it's all the input image. So going between 0 and 1, you get, starting at 0, it's all the input image, and ending up at 1, it's completely noise. So we get the same thing as the effect of the scheduler, if you will, but there's no scheduler concept. It's just choose a value between 0 and 1, and based on that, add the amount of noise. Then that's the simple, this is, if you will, the simplest illustration of the noisify function. So corrupt means choose a noise, which is, and again, the one important thing to notice is, unlike in the previous notebook, he uses rand, so it's not a normalized noise. It's rand instead of random. That's the difference. That's one difference. And then, you obviously need to make the amount or whatever the noise you're adding because of the broadcasting rules and stuff. You need to make it have the same shape to make broadcasting work. And then as the image that is the same shape to the noise that you're adding or multiplying amount by. So you make amount have this shape as well, and then do the x 1 minus amount noise time. That's the simple definition, the simplest noisify, if you will, I guess. And then you just look at the results, plotting the data, right? So this is the input data, and then as you increase the amount, and that's what you do by basically this, right? You just increasing the amount from 0 to 1. When it's 0, it's all input. When it's 1, it's all noise. And between them, you have various amounts of noise. That's what is shown here. This is 1 for the amount, so it's all noise. This is 0 for the amount, so it's all input image and various amounts of noise. Then you do this model. He uses, this is an illustration. By now, we are familiar with UNet. He builds a very basic UNet just using convolutional 2D, not even this 2D blocks from diffusers, but just on 2D, the down layers and up layers, no attention, none of that. Downscale, upscale, just max pooling, upscale and upsample with a scale factor of 2, and just do the forward. But again, because we need the stored layers, so you use the list to do them. And you pop and add. Make sure that it gives you the same shape of the output as the input. This simple UNet that we have built comes with about 300,000 parameters and train the network. So you just add batch size, data loader. Again, you can see all this is done in PyTorch very simply. Box only, move the thing, define the loss function is just MSE loss. We've learned all the ways in the last lecture we discussed from journey of 4 different losses in a full-fledged when we are training latent. In this case, we just use the simplest which is kind of also called the reconstruction loss. And you define the optim parameters and then, do the flow, move the model to the device, add, again, not random, not random 0 to 1 Gaussian noise, but just random noise in the shape of the image. So that this result can corrupt the image with a noise amount, predict the, use the model, give it the noisy X to the model, get its prediction, calculate the loss, use the optimizer to go back, step, and then just save the losses so you can print them. We're just printing it for 3 epochs, and you see plot, and then you can see what the model predictions look like. And you have the input data, you have the corrupted data, and the predictions. And you can see also, again, as we saw in story detail in Yami's notebook, what happens when noise gets to be really high. When the noise is, and we've seen these like up to about, I don't know, maybe this is in the 40th percentile range of between 0 and 1 of noise added, so it's still able to recover. But look at, and even here it's able to recover somewhat. You can recognize that the digit is 6, but then look at these two, and you just see it's just spitting out some average image. So when the noise gets to be really high, it struggles to see what the image is in the buried stuff. So that's what he calls out, that when the noise is low, the prediction is pretty good, but as the level gets very high, there's less. And by the time it gets to 1, it just outputs a blurry mess close to the mean of the data set, because that's the best you can do when just use MSE loss. And this is, in fact, the reason why we add these, tail divergence laws and the Gannett laws and all these kinds of things to improve it, because otherwise it just tries to mimic the mean, because that's the only way it knows to approximate the MSE loss. And then this is going in the reverse direction. So how do we generate the image? Once we have these set of images which are noised. And so what he does here is, again, without, now we don't have a scheduler or any of that kind of stuff. So all he does is denoise a little bit, again, provide that denoised input as the next set of input, and go through one more denoising step, repeat a few times, and hopefully it all goes, we get an image up. And here he just uses 5 steps. And the predicted denoised images at each stage. And over a few steps, we see the structure get refined until we get a final. So the number of steps in this case is, think of it as equivalent to the 1,000 steps in a diffuser time step scheduler, but we don't have any kind of scheduler in this case. We just add some amount of noise in our corruption process, that corrupt function that we have defined. So that's the sampling in this case, define the number of steps. We just start with random value for X and predict the output history. So predict using the model, store the model output for plotting, use this mix factor, right? How much do we move towards the predictions? And then we just use that mix factor to move a little bit towards what it's predicting, but not all the way there, because that's what helps us kind of repeatedly iterate and store the steps. And so the first time we start with, noise, it gets that, and then we provide that as the input to the next step. We get a little better, do that again, and do this a whole bunch of times, you can kind of sort of see some images, but obviously even it's not using a scheduler, it's not using a lot of things that we are by now familiar with what's required. And therefore we just kind of sort of see some numbers, but these don't look anywhere close to the actual numbers that we have provided the model as a starting point instead. And then obviously we took 5 steps. That's all we did here. So we can take 20 steps, see whether that improves, and you can see it does improve some of the numbers much better than before, but still pretty poor. And that's when you say, well, let's, this is extraordinarily simple and fundamental in what we're trying to do, because we want to kind of understand the basics of what we are trying to do. But then we use something like a DDPM scheduler and the DDPM method. And here are all the ways that that's much more complicated and complex. And what we have tried so far, first of all, our unit model was just a fun 2D model. It doesn't have attention. It doesn't have ResNet blocks, none of the complicated or complex, none of the more interesting things. So the diffusers unit 2D model has all of that. The corruption process is handled differently because we use schedulers. So there is a precise amount of noise corresponding to the time step that gets added. The objective is different. In this particular notebook, the model that he uses it to predict the noise image. So it's both the structure of the image as well as the noise. Whereas, we've seen in DDPM what the model is actually predicting is just the noise rather than the noised image. Then you also condition the model on the amount of noise that's present based on the time step. So the time step is also passed as an additional argument. Remember the discussion we had about passing tuple, both the input image and the time step, which is again converted into an encoding and embedding and mapped into the sine cosine functions, and all of that kind of complexity is added to it as well, which we completely lack in our extremely simple steps we took. And then a whole bunch of different sampling strategies too, right? We have seen this, the Euler ancestral, the Hume, all these different ways by which you interpolate or extrapolate between what you have available. And that's, again, not something we did. So these are all the ways in which the DDPM is much more complicated than the simple steps we have taken. So that is how, and then obviously we have seen beyond DDPM, there's DDIM, and then there's this whole design space paper that we implemented as well. So he just says, those are all the ways in which things are better. And just looking at the unit, here are all the ways that the unit that we use from DDPM for diffusers library is more complicated compared to the very basic on 2D unit. So here he doesn't even use a couple of down blocks, just one down block, a couple of attention down blocks, and get a couple of attention up blocks, and then a single up block, and you can print it and look at what they are, and they use the ResNets and so on. And after that, kind of basically compare the unit model that he has created to the unit model that now are using, and you can see 1.7 million parameters versus about 309,000 parameters. And it tells you the complexity of the model. It's about at least 5x larger, if you will, in terms of the number of parameters. Then you can replicate the training using this model in place of original, and we again only train for 3 epochs. Train this model. Again, very simple training. Don't do anything fancy. So basically using PyTorch, no mini AI, no callbacks, no fancy initialization, by the way. If you notice, we haven't done any initialization of the unit either. Also an interesting difference compared to what we saw. And then if you do that and generate the samples from it, you can see this is definitely much better than what we saw here, where we did 40 steps. This is the best output we got. Again, one way, I guess, to really quantify this is to potentially use FID and KID. Import that code and try to use that to see what type of FID scores we get. And these numbers look a lot crisper. So that's for sure using just the improvements in the unit, we see a much better result. And then he talks about, how the corruption process is different and how it's defined. We are very familiar with this by now, that you do the mean is square root of alpha bar and the variance is square root of 1 minus alpha bar. And this is the cum product of the alpha bar t if we want to go all the way from 1 to t instead of doing it step by step. And all of this detail is obviously hidden behind the scheduler. You can kind of see the code for what the add noise function of the noise scheduler does. And this is the traditional beta bar, the beta bar max values that we use, which are default values. But then we also saw the cosine scheduling, and also varying the beta start and beta max, and how it kind of varies with the noise and how it adds different noise. Scheduler is what determines the amount of noise added. Well, and that's it. He just kind of shows you that the DDPM version, as I was highlighting, the DDPM version adds noise from a Gaussian distribution. So it adds it from a rand end, if you will, rather than the uniform noise which we have been adding, which is just the rand, dots.rand, what we used in the corrupt function. And in general, it makes sense to normalize the training data as well. And you saw in the first notebook, we did this normalize 0.5.5, but as I was mentioning, another interesting thing to try is, instead of just using the normalize 0.5.5, normalize it to, which normalizes it to the range of -1 to 1, try to normalize it to the range of -0.5 to 0.5, which apparently gives a better result. So we ought to try that as well. We didn't do this for this notebook, but this visualization thing does that. Adds that. Then it is, we just did the very simple training and we tried to predict the denoised image. That's not how DDPM and traditional diffusers work. They actually predict the noise. In DDPM and many other diffusion, the model actually predicts the noise used in the correct. It just gives you the code. And it kind of goes into a couple of different paper references as to why. And then the last paper that Jeremy discussed as well, which is the using design space of generating models. And he again guesses here that maybe at some point in time, we may get to the stage where the time step input is no longer required. But I haven't seen any papers. I haven't looked for them specifically, but I'm not sure whether there are any papers which tries to get rid of this, given that I just posted the four-step process, and even in that case, there seems to be a time step involved. So that's why they're talking about number of steps, right? 4 steps. So I think in that sense, I'm not sure whether this prediction is true, at least yet, that we can get good predictions without including time steps. That doesn't seem to be the case up now. And then he talks about the fact that time steps are also provided in conditioning, and all these variations on how we sample. Oh, and the relevant docs. So that's it. Any questions on just this? They have like couple of notebooks to go through in the next unit 2 as well, and it has an attached video. That too, that I'd encourage you to play with. But I thought this was a good revision as well as a good exposure to the pipeline and using the pipeline of diffusers.
So I think we covered at some point, but the model's trying to predict the noise in some cases instead of the signal. Is that
instead of the noisy, it predicts. In this case, he tries to train he's training a model which predicts the noised image itself rather than just the noise. So you add the noise to the input to the clean image, and then you have the network try to predict the noised image, not just the noise in the image. So you're trying to predict noise plus image in one case, and in the other case, you're just predicting the noise.
When you are predicting, when the point is to predict the noise, is that, or the approach is the reason there? What is it? Is it memory or why? What's the advantage of doing that?
He discusses that here. Let's see. Estimating predicting the noise equivalent to just predicting the denoise. So why favor one over the other? Right? And he talks about the subtlety, which I didn't frankly completely understand, but he says that obviously we predict the loss across different randomly chosen time steps that we know. And these different objectives, which basically by that he means that since we're adding a random amount of noise, depending on our choice of the time steps, because the time steps are chosen randomly, and then corresponding to the time step, depending on the scheduler, we add different amount of noise, right? Now, he says that when we do this, it will lead to different implicit weighting of these losses, where predicting the noise puts more weight on lower noise levels. I don't quite understand what that means.
And it sounds like there are other ways to achieve that too with the scheduler. Is that right?
Yeah, see, because he also says you can pick more complex objectives to change this implicit loss weighting. First of all, I don't understand what he means by different implicit weighting. I don't understand the term implicit weighting.
Yeah.
It just seems. So I did some very preliminary search, but I have to dig more to understand. I don't have a good grasp of what he means by implicit weighting of these losses, because corresponding to the scheduler, you add some noise. So what he means by implicit weighting is lost on me. And the part that where he says predicting the noise puts more weight on lower noise levels.
Yeah.
Why? I don't get that. And he says perhaps you can choose a noise schedule that will result in more examples at a higher noise level. That is just a matter of changing the graphs we saw earlier, right?
Mm-hmm.
If the shape of the graph is different, then obviously the number of time steps at higher time step numbers will be different, which means that correspondingly the number of examples chosen where a lot of noise is added will be different. So maybe that's what is meant by implicit weighting. That is, the number of samples you chose at different weight levels depends on your scheduler. And now I'm just talking through this myself, but basically it seems that is governed by the shape of your scheduler curve, right? And if but that then just simply means that you change the schedule. That doesn't, in a sense, answer the question we started off with, the question you asked, which is, why is predicting noise better than predicting the noise image?
Mm-hmm.
Right? So he tries to answer that question here, but I'm not sure that he actually did. And here's something else he mentions. Right. Perhaps you have the model predict a velocity, which will define as being a combination of both the image and the noise, depending on the noise level. And that's apparently covered in this paper, Progressive Distillation of Fast Sampling of Diffusion Models. I haven't looked at this paper. And then he also says, perhaps you have the model predict the noise, but scale the loss by some factor depending on the amount of noise based on a bit of theory. And there's another paper on that based on perception prioritized training of diffusion models. And then there's another way, which is purely based on experiment, trying to see what noise levels are most informative to the model. And that's where this elucidating the design space of diffusion-based generative models. So he just says at the end, TLDR, choosing the objective as an effect on the model performance. That's kind of the simplest answer seems to be, hey, depending on what loss we choose, it makes a difference, but that's not explanatory, right? That's just stating the fact.
Sure. No, that's still helpful though. Maybe I'll check out some of those papers.
Yeah, and then it says that its research is ongoing as to what the best option is. So it's a very good question. It doesn't seem to be that people exactly know what the answer is.
Oh, okay, thanks.
Right, and then you see this at the moment predicting the noise, the favored approach. But over time, we may likely see other objectives used in different situations.
Interesting. Thanks.
Yeah, so if you see anything interesting to post on Slack, I'm interested in kind of why and what as well. Cool. Any other questions or thoughts? If not, we're done early, and thanks for joining. Till next week. in the Kaggle meeting an hour from now.
All right, thank you so much.